or the row 4 of the transformation matrix defines the origin, and the local x, y, and z axis define the coordinate system's x, y, and z axis. This is what happens internally when you pick a node as the reference coordinate system, or when you link one node to the other and transform it in its parent space. Let's assume that after having this first teapot rotated at an arbitrary angle, we want to create another teapot with radius of 10 units and place this teapot at exactly 50 units above the first teapot. That means 50 units along the positive z-axis of its local coordinate system. It is relatively easy to place an object at 50 units in world coordinates, but it appears to be relatively difficult to figure out where the 50 units above the first teapot would be. Luckily, using matrix transformations, this is one of the easiest things to do. We're going to multiply the position 0050, which is normally in world space, by the transformation matrix of the first teapot, which actually converts the coordinate system, replaces the world coordinate system with the user coordinate system of the first teapot, and places the second teapot at exactly 50 units above the origin of the new user coordinate system. This didn't reorient the teapot, it only moved its position, because we multiplied a vector and not the whole transformation matrix by the user coordinate system, the local coordinates of the first teapot. We could first set the coordinates of the second teapot to 0050 and then multiply the complete transformation matrix in order to transform from world into user coordinate system space. In this case, not only the position changes, but also the orientation and the scaling. For example, if this teapot was scaled locally along its z-axis, and we would perform the same transformation as before, the new object is going to acquire the complete transformation of its user coordinate system. Not only can we transform into the coordinates of an object, we can also transform back into world coordinates, into world space, by multiplying the transformation matrix of the already transformed object by the inverse of the user coordinate system's transformation matrix. This is the opposite of transforming into the space of the first teapot. We're going to take the object and transform it back into world coordinates. As you can see, the position along x and y has a small error, but it's very, very, very close to 0 in world space. This means that we can multiply vectors with matrices, and this would convert the vector into the coordinate system of the matrix. Or we can multiply complete transformation matrices by other transformation matrices in order to convert a complete transformation into a new coordinate space. MaxScript provides methods for creating transformation matrices